Hey everyone, welcome to Real Analysis 1. This is going to be lecture 1 of the course. And in this section, we're going to get started by reviewing some of the kind of preliminary concepts that will be needed for the course. So specifically, we're going to discuss sets and functions. Now you will undoubtedly have seen these things before, but we're going to level set here by kind of pointing to all of the things that'll be necessary to know for the course, as well as potentially dealing with these things with slightly more rigor than what you've maybe seen in the past. And that, of course, varies depending on what your background happens to be. But so let's go ahead and get started. And we'll call this section 1.1, Sets and Functions. Okay, we'll start with sets. Okay, so this is going to be kind of it'll be kind of conversational in nature here, but really what we need to do is just make sure that we all have a good sense for how to think about sets and and have a good sense for what the fundamentals of set operations and such are. So sets are obviously going to be encountered pretty much constantly in mathematics. We talk about sets of numbers, we talk about families of functions, which is another way of saying a set of functions. We talk about sets of objects, collections of objects, etc., in abstract algebra, for example. So we really can think of a set as just a collection of definable objects. Right, so when we talk about a set, we're really talking about a collection of definable objects. And there's some notation here when we write something like this. What that means, of course, is that X is an element of the set A. And if we write something like this, that means X is not an element of A. Right, and so basic set membership is something I'm sure you'll have seen, but we're making sure that everybody's on the same page here. There is a concept of an empty set. The set containing no elements is called the empty set. And we denote it well, there's different ways to denote it, but most often we'll use just this symbol here. There's different ways to define sets. You can, just list the elements of the set, so we could write things like this: A is equal to the set -1, 2, 3, and 4, for example. Right, in the case where it's just a small finite collection of elements, we can do something like this. We can also list the elements of an infinite set by using this convention of the ... dots. And so this will be something you've probably seen. So this indicates obviously that we're talking about the entirety of the integers. So we obviously can't list all of the integers as there are infinitely many. But the indication here is that the pattern continues in either direction. So this would be like just listing the elements of a set. We can also use something called set builder notation. Right, and so we might say something like this: A is equal to the set of all X, such that X is equal to 2 times N, and N is a integer. Right, and so something like this, and of course this would be equal to the set ... -6, -4, -2, 0, 2, 4, 6, ... right? So two ways of writing the same thing there. Okay. Another example would be something like this. C is equal to the set of all x such that x is between 1 and 100. All right, so of course this would be just the set 1, 2, oh, and maybe we should say x is an integer as well. 1, 2, 3, and so on up to and excluding 100. Right, notice the inequality there. Okay, so these are just different ways to write sets. So I'll assume that you've seen some set theory in the past, and we're just kind of refreshing our memory on a couple of these things. There are some very key sets that we'll pretty much be constantly referencing as we go through analysis here. So key sets would include, and you're going to be familiar with all of these, but let's just level set on this, the natural numbers. That's the set from 1, 2, 3 to infinity. We call these the natural numbers. Okay, so you'll have seen that for sure. I've certainly heard of them. The integers. So that's going to be your -3, -2, -1, 0, 1, 2, 3, ... That's the integers. All right. And the other set that will be very important is the rational numbers. So this is going to be the set of basically fractions. So we'll write it like this. This is going to be the set of all PQ such that P and Q are integers. Okay, and also Q is not equal to 0. So these are the rationals. The rational numbers. Okay, so these are all sets that you're very familiar with. And then, of course, since we're talking about real analysis, we're going to be talking about the real numbers. And for those, I'm just going to write the real numbers for now. And so that's the set. Okay. Now, a lot of what we'll be doing in analysis is describing what the properties of the real numbers are. And indeed, that's going to be a big focus of the first part of the course, is talking about, what does the continuity really mean in the real numbers? What is, what is the topology of the real numbers, etc. We're going to get into all of that. And so this is going to be a key focus for us, this describing, characterizing the real numbers. Okay, so we can start with a few things that we know about the real numbers, though. We know that Q, the rational numbers, are a subset of the real numbers, right? And so specifically, Q represents all of the real numbers that can be written as fractions. So Q is the subset of R that can be written as, fractions, basically. The ratio of two integers. There's going to be another subset of R that obviously then doesn't have this property. And so this is what we call the irrational numbers. Numbers that can't be written as the ratio of two integers. And we'll frequently denote this as R minus Q. Right? And so obviously, so the irrational numbers R minus Q is the set of real numbers that cannot be written as the ratio of two integers. Okay, so you're familiar with some of these. Pi, for example, is an irrational number. Okay, so pi is an irrational number, and there are indeed infinitely many, right? So, obviously, it's true then that R is equal to the rational numbers union the irrational numbers. Okay, and so we'll talk about this notation a little later, but it's the set of, if you take all the rational numbers, you take all the irrational numbers, you put them together in one set, you've got the real numbers. Okay, we'll come back to this. We'll circle back. This is just a, hey, you probably will have heard of this, and if not, you should be thinking about this a little bit at this point. We'll get into more details later, of course. But and if you have heard of it, just a reminder that there are such things as irrational numbers, and there are such things as rational numbers, and together they form the real numbers. Now, let's think about the rational numbers a little more. All fractions can actually be used to represent a given rational number. So it is possible to represent a rational number in a variety of ways. And I don't mean anything cryptic here. Obviously, it's just true that 1/2 is equal to 5/10, which is equal to 10/20, and so on, right? And so we'll frequently, in acknowledgement of this fact, we'll frequently resort to the following test to determine whether two rational numbers are equal. So if we say that the first rational number is P1/Q1, and the second rational number is P2/Q2, then R1 equals R2 if and only if P1/Q2 equals P2/Q1. So basically, if you cross multiply and divide here, you should get equality. So for example, 5/10 equals 10/20, and I know that because 5 times 20 equals 10 times 10. So 100 equals 100, right? So that's going to be the test that we'll frequently make use of. Okay, so just pointing that out. I mean, it's a fact that many of the rational numbers really represent the same quantity, right? And so we'll need a way to distinguish we'll need a way to determine when two rational numbers are identical, and this is going to be the test we'll fall back on. Let's talk next about, let's jump into sets a little more. So let's talk about the concept of a subset and containment. So we say that a set A is a subset of a set B, or we might say A is contained by B, or A is contained by B. We usually write something like this, which we've used the notation already up above. But a set A is a subset of a set B, or A is contained by B, if every element of A is also an element of B. Okay? And so that's the concept of a subset. A is a proper subset of B. A proper subset of B. And we would denote that usually by A and then a subset, and then below it like a not equal symbol. So A is a proper subset of B if A is a subset of B, and if there exists some element in B such that that element is not in A. All right. I mean, it's just another way of saying, hey, look, A is a proper subset of B if A is a subset of B and it's actually smaller than B, right? There's additional things in B that are not in A, and that's all this is. That's this concept of a proper subset. We'll use that all the time. Okay. And now, importantly, and this will come up all the time in the proofs that we're writing, right? Two sets, A and B, are equal if and only if A is a subset of B and B is a subset of A. Okay. Right, so in order for two sets to be equal, basically the proof of equality of two sets is to show that everything in A is in B, meaning A is a subset of B, and also show that everything in B is in A, namely B is a subset of A. So A is a subset of B, and B a subset of A implies A equals B. Actually, and so this is if and only if, so the implication goes both ways. Okay, and so we'll see that in a second. We'll use that. And then we say that the empty set is a subset of every set. The empty set is a subset of every set, right? So for all sets A, the empty set is a subset of A. All right. Okay, so let's go ahead and, that's kind of, I know that was sort of quick, and as I said, it's kind of conversational, not controversial, conversational. But again, the assumption here is that you've seen some set theory, you've had it in other courses, and I think it's unlikely you'd be taking, seriously taking a real analysis course without having some idea of what subsets are and sets and things. And so we're just reviewing and kind of making sure everybody's on the same page. Let's talk next about set operations. Set operations. Okay, so things like unions and intersections, right? You will have seen this, but let's review this. So the union of A and B, and it's denoted by A or B. This is the notation. This is the set of all X that is in A or in B. Okay, so we would write it like this: A or B is the set of all X such that X is in A or X is in B. Okay, and if we were to think about this in terms of a Venn diagram, I've got two sets, A and B. A or B means it's in A or it's in B. Right, so at this point we're talking about basically everything in either of these sets. And of course the implication there is that it can be in both at the same time. So that's the union. Okay. What about the intersection? The intersection of A and B, denoted by A and B, is the set of all X that is in A and in B. Okay, so A and B is going to be equal to the set of all X such that X is in A and X is in B. Now, of course, up here we were talking about the or, and now we're talking about the and, right? And so again, if we were to think about this from the standpoint of a Venn diagram, this is, in order to be in A and B, you have to be in A and in B, right? And so that means we're talking really about this little section here. That's the intersection. All right. And again, I anticipate people will have seen this. I anticipate that this is not new. Okay. And then finally, the only other one I think that we really need to talk about is the, well, before we jump there, let's mention this. Two sets, A and B, are disjoint if the intersection is equal to the empty set, right? So this would be the scenario where I've got A and I've got B, and there is no overlap, right? So the intersection here is empty, right? And so this will come up a lot, and we'll use this in a lot of proofs, you know, when we're talking about analysis, when we're getting into real analysis, we'll use the idea of, you know, frequently a proof will basically boil down to showing that two sets are disjoint, for example. Okay, and so what we're talking about there is that the intersection of the two sets is empty. All right, and so just a related concept to intersection, of course. Let's talk about the complement and the relative complement. Okay, we'll start with the relative complement. The relative complement of A and B is the set of all X that is in B but not in A. This may be one that you're less familiar with. If you've had just basic set theory, you may not have encountered. This one may not have been something that you worried too much about. In symbols, we would say B minus A is equal to the set of all X such that X is in B and X is not in A. You will definitely have heard of the complement, but the relative complement is just a slightly different concept here. I mean, the complement is basically the relative complement of whatever set you're looking at and the universe. So this is a relative complement, means it's the complement of a given set with another given set, not necessarily the universe. And so if this is A and this is B, then B minus A would be the relative complement of B and A, would be everything that's in B but not in A. So we would be talking about this chunk over here, wouldn't we? Okay. And then, of course, if you have heard of the complement, you maybe have heard of just the complement, not the relative complement. So if A, and for that we would say if A is a subset of some fixed set X, and then here I would say representing the universe, i.e. all of the elements under consideration. So if A is a subset of some fixed set X, rather than write X minus A, we would just write A complement, slightly more abbreviated. So A complement would denote, the set X such that X is not in A. Right? And the idea here, of course, is that X is in the larger set X, but it's not in A, right? So sort of under the, being left out here is the idea that X is not in A, but of course X is in X. It's the universe, right? So just a little shorthand, right? Just to make sure that, I also want to just make sure that people get the concept of a complement and a relative complement. Okay. All right. So that's all introductory. What we want to do next is I want to lay out some of the key theorems of set theory and some of the key concepts from set theory that we will need for the course, and prove a few things just as a matter of example of how to prove things with sets. So the first theorem I want to talk through is basically it's basically De Morgan's law and the distributive laws for sets. So if A, B, and C are sets, then the following. So first, A and B or C is equal to A and B or A and C. Okay, so this is like the distributive laws, right? So you could think of sets as distributing across these operations. So A and B or C is the same thing as A and B or A and C. Okay, and then the reverse idea would be A or B and C is equal to A or B and A or C. Right, so these two together are what we would call the distributive laws. Okay, those are the distributive laws. And the other two are as follows. So the first one would be C minus A or B. Right, so this is the relative complement of C in A or B. This is going to be equal to C minus A and C minus B. And then the other one would be C minus the intersection A and B. That's equal to C minus A or C minus B. Right, and these two are what we call De Morgan's laws. Okay. Very good. So we'll use these a lot. I mean, we'll reference these constantly whenever it's unlikely that we'll even encounter a theorem where the proof essentially is a set theory proof where these aren't referenced. These are very commonly used. And so let's prove the first part of this. So we'll prove 1, and the others will be similar in proof. So for this, we want to show that A and B or C is equal to A and B or A and C, right? And the goal here is just to kind of, well, to prove it, but then also just to illustrate the method of proof that we'll be using whenever we have to prove something in a set theoretic way. So remember, to show that two sets are equal, this set, we have to show that this set is a subset of over here. The left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. So we'll first start with showing that this A and B or C is a subset of the other, right? So we'll show that A and B or C is a subset of A and B or A and C. Right, so we need to show the containment in this direction. And really the way to show that something is a subset of something else is to take an arbitrary element from this set and show that it must also be over here, right? And if you do that, then you show, because the element you've chosen is arbitrary, you've shown that the containment is true. So let's let X be an element of A and B or C, right? And what does that imply? Then basically it implies that X is in A and X is in B or C. Okay, that's all that means. Sorry, one second here. Yep. Okay, so since X is in B or C, that means that X is in B or X is in C. Okay, and kind of two cases are up. So if X is in B, then X is in A and B, right? Because X is in A and it's in B or C, right? If X is in C, then X is in A and C. Okay, and so either way, X is going to be in A and B or A and C. Okay, and that's exactly what we want to show up here, right? So A and B or C must be a subset of this, of A and B, or A and C. Okay, so that's the one direction. Right, so a lot of, these are very, these are just logic. It's just, it's just read that what the set is, and X is in A and B or C means X is in A, definitely, and it's in B or C. And just break it apart and reassemble it. And it's very, very straightforward. So let's do the other direction. So now we need to show that A and B or A and C is a subset of A and B or C. So we need to go the other direction now. So let's let X be an element of A and B or A and C. Okay, and so the implication then is that X is in A and B, or X is in A and C. Okay. So if X is in A and B, right? If X is in A and B, then X is in A and X is in B. Okay. Right? And what this implies then is that X is therefore in B or C, right? It's in B. So it's in B or C then. And similarly, if X is in A or C, or sorry, A and C, if X is in A and C, then X is in A and X is in C, and that's going to imply that X is in what? B or C, right? Okay. And so X is in A and B or C as desired, right? So that's really the key. Okay, and so that means the reverse containment is true as well. So A and B or A and C is a subset of A and B or C. Okay, so you've got this one, and you've got this one, and so together you get the result that the two sets are equal. Okay, we'll say that's the end. Okay, so yeah, you could, I would recommend going through this one and really making sure that every single line just makes perfect logical sense to you, if it doesn't already. It's imperative that you be able to reason about sets at least at this level, right? So I think these are fairly straightforward, obviously, but if not, please be careful and make sure that you understand how to think about these set theory proofs. And I would recommend going through the other three as well. All of them, they all kind of work the same way, right? It's all just a matter of, since you're trying to show equality, it's all just a matter of breaking the statement apart and then reassembling it, showing that you can reassemble it in the desired form. Okay, very good, very good. Let's keep moving forward. Okay, let's keep moving forward. The power set. Let's talk about the power set. We'll use the power set ideas. So if A is any set, then the set of all subsets of A is denoted, well, usually we use some kind of a script on this P, but it's basically a fancy P of A, and this is called the set of all subsets of A is denoted by this, and is called the power set of A. power set of A, right? So simple example would be like if A is equal to the sets of elements 1 and 2, then the power set of A is equal to the set of all subsets of A, right? So the empty set is a subset of all sets, so that's there. And then you've got, well, what if I just have 1? That's a set. What if I just have 2? That's another set. And the whole thing is a third set. Okay, so this would be the power set. Okay. Another example maybe, let's see. Let's say B is equal to the set 1, 2, and 3. Then the power set of B is equal to the empty set, the singletons, and then because there's 3 elements, it's not just the whole set automatically. You've got the doubles, so you've got 1 and 2, 1 and 3, and 2 and 3. And then, of course, you've got the whole set, 1, 2, and 3. Okay. And so up here we see that the size of the power set of A was 1, 2, 3, 4. And down here we see that the size of the power set of B is 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, indeed, it can be shown that the size of the power set of a set A is equal to 2 to the n, where n is equal to the size of the set A, the order of A. Okay, so for example, up here, the order of A is 2, and so there are 2 to the 2 squared elements in the power set, 4. 2 times 2 is 4. And here, the set B has order 3, right? And so there are 2 to the third. 2 times 2 is 4, times 2 is 8 elements in the power set. So this is a proof that we'll be looking at later. But very elegant, right? The set of all subsets of a set called the power set has this nice property that the number of elements in the power set is equal to 2 raised to the power of the set of the order of the set itself. Okay, let's talk next about a concept that we'll need for when we discuss functions, and that's the Cartesian product of sets. Okay, so if A and B are 2 sets, the Cartesian product of A and B, and we denote it by A cross B. Okay, the Cartesian product of A and B, A cross B, is defined as the set of all ordered pairs A comma B, where A is from the set A and B is from the set B. Okay, so in symbols we would write A cross B equals the set of all A and B ordered pairs such that A is in A, B is in B. All right. And so you can think about, well, let me switch pages here. So if I've got A cross B equals the set of all ordered pairs AB such that A is in A, B is in B, I can think about this in terms of visually like this, right? So let's say I've got 2 axes, and on this axis I define this region here, which is the set A, and on this axis I define this region here, which is set B. Then the Cartesian product of A and B is going to be the space in this 2-dimensional plane where these two sets overlap. This is A cross B. Right, and so for a specific element, maybe little a here and little b here, that element of A cross B is going to reside in the given set at this location where those two intersect. Okay, so you can see that, right? That kind of is clear. Okay, now of course we've seen this. We use this all the time. Really, the Cartesian product of R with R is called R squared and is known as the Euclidean plane, and we've seen that, right? So the Cartesian product of the real numbers with the real numbers, we call it, well, it has a couple different names. We sometimes call it just the plane, but we also call it the Euclidean plane, or we also refer to it as R2. Right, and if you've been doing algebra, graphing things, you've been implicitly using the Cartesian product concept, right? Though you may not have referred to it in this way, and you probably didn't think about it in set theory terms. But for this course, we will need to think about it in set theory terms. It just makes constructing a lot of the proofs and getting at a lot of the ideas of set theory much easier. So a simple example, right? If A is equal to the set 1 and 2, and B is equal to the set -1, 2, and 4, then A cross B would be so how many elements are going to be in the Cartesian product? It's going to basically be 2 times 3, so there'll be 6 elements. Okay, half of them are going to start with a 1, and the other half will start with a 2. Okay, and then for everything that starts with a 1, you'll have these. So -1, 2, and 4, -1, 2, and 4. So this would be the Cartesian product of these two simple sets, A and B. Okay. All right. Very good. Okay, I think I'm going to break this lecture into 2 parts. So this would conclude kind of the set theory part of it, and then the second half will delve into functions, but using the set concepts that we've just discussed more explicitly in the derivation of some of the ideas of functions. So we'll be right back with part 2.